So we are still in chapter 13, which is covering policy gradient methods. And we had already covered um, reinforce with baseline, and actor-critic methods in the discounted return case. And typically these techniques would be used for episodic problems. Those are the examples we've used so far, but you could also, we are using a discount rate, so we could use these for continuing problems as well. But in the case of approximation, in a previous chapter, we had talked about using an alternative performance metric for continuing problems. So yeah, so for continuing problems, we introduced the average reward as an alternative to the discounted return. And this is the definition of it is exactly what you would expect, which it's the sum of the expected return at every time step, averaged over all the time steps. So this is out to some time horizon h, and we assume the problem could go on forever. In theory, then this, 1 over h times this is just taking the average. Now, if in fact this expected value exists, you can show that instead of taking this 1 over h in this sum, you can just take the limit as t goes to infinity of this expected value. But that is only possible if this expected value exists. There are problems where, for example, you would get a repeating reward sequence that would be completely deterministic. And in that case, there is no expected value of the reward, which is independent of t. It would keep oscillating. So if this condition holds, this expected value exists, then you can also write this in terms of the steady state distribution. And these things should be equivalent if we know like the probability transition function, and this is just summing over all the states, and it's weighting this quantity by the probability of being in that state. And this average reward is defined for a particular policy. So here you actually see the policy distribution explicitly in the expression. And then the only thing that isn't a probability here being summed is R. So this is just computing, this average reward, and it's summing over all the relevant quantities and weighting it by the appropriate probability. So in a problem like this, the goal would be to maximize the average reward per time step. And whereas before we started with the discounted reward, now we're going to try to rederive the policy gradient theorem, but in this continuing case using this performance metric. And in some ways, the derivation is actually easier than the episodic case because you don't have this this sort of counting problem of needing to count all the state transitions. There's a little bit easier way to do it. And this was also from, I believe, chapter 9, but the steady state distribution mu obeys this relationship where we can express mu at some transition state in terms of the sum over all states, right? So mu is this is sort of like saying that, mu is unchanged by applying this operation to mu. So this will come in handy later on in the proof of the policy gradient theorem. And then all the value functions that we had previously defined. So, we had typically like the value function is just the expected value of g, where g is the discounted return. But in this case, we have a new version of g, which is the differential return. So instead of discounting all of these rewards by some, exponentially decaying factor, and so that the sum converges, now we're going to force this sum to converge by just subtracting the average reward at every time step. So as this sequence goes on, you'd expect these later terms to all cancel out to 0. So really what this g is measuring is the sort of difference in reward from the average in the early part of the transitions from this state. Right? So this G would always be from, at some time step. So whatever state we're in that time step, it's going to affect these early rewards. And then the value function that we define, like V, is called the differential value function, as opposed to the discounted value function. So it still depends on the policy, but we can only compute this if we actually have an estimate for this value, right, of the average reward. And you could imagine, like, over the course of an episode, there's different ways of doing it. You could just directly keep track of the average by averaging the rewards you've seen, throughout the training process. Typically, this quantity is actually, we keep track of it with some bootstrap method where we're using some existing estimation function for the differential return. But you'll see that in some of the algorithms. So these definitions all set up the preliminary groundwork that we need to to prove the policy gradient theorem in the continuing case. So are there any questions about these definitions and the new performance metric as compared to the one we've been using so far? Okay, so you can just look a little bit at the policy gradient theorem proof in the continuing case, where we want to end up with an expression, which is something that we can actually calculate the gradient of, that's possible to do on every step, in this case, in a continuing problem. So we're going to have to, manipulate a few things, because it looks like at first, like, there's no obvious formula for whatever the gradient of this average reward would be in terms of the policy parameters, right? Like, that was the same problem we had in the first case of the policy gradient theorem, where it looked like our gradient would, end up depending on this on policy distribution, which we don't know ahead of time, and it's hard to calculate, especially if our policy is changing throughout the training process. So, to start out, it looks like a little arbitrary, because we're not going to actually start with trying to directly compute the gradient of the average reward. Instead, we're going to write down an expression for the gradient of the differential value function here. So here, so far, it just looks like the expressions we had for the discounted value function. Right? We can always express the state value function in terms of the state action value function, as we do here. But these, in this case, whenever these value functions are written down, these are the differential value functions. So here, this is just applying the product rule to this expression and bringing the sum, outside of the gradient term. So we have, two terms here. And the first term we're going to expand is the second term, where now we have the gradient of the state action value function. And we're going to then expand this. So at first, we express the state value function in terms of the state action value function. Now we're going to do the reverse and replace the state action value function with this expression. And this is using, the definition of the differential value function. And, this probability transition function is part of the environment that you're in. So this is the reward that you would actually see in the transition. And this reward function, which has the big theta in it, because this is the average reward, this single value, which depends on theta, which are the parameters controlling the policy function. And then this is just the differential state value function at the transition state. So now we can distribute this gradient back into this expression. This first term with R, none of these terms depend on the parameters, so we can just ignore it and set it to 0. So the two remaining terms, now we just have the gradient. We can bring the gradient inside of here because the probability transition function also does not depend on the parameters theta. So fine, we've manipulated this expression. And now the whole point of doing this is like there's still this sum over A on the outside of this. But if you notice, like R, the average reward gradient here, it doesn't depend on A at all. So if you look at this term, we end up having this sum over A of the policy function. But the policy function is just a probability distribution over the actions. So this will end up being 1. So what we have here, we've actually isolated an expression for the gradient of the average reward. I have just a little explanation here. See that right here, this term is the one in the middle here. We have the sum over A of this and the gradient of pi, and we can actually just completely factor this out of the sum, and then we just have this, which reduces to 1. So here, this expression is equivalent to this, and then we can just swap out the position of these, or we can move, this is the expression we're actually interested in computing, which is the gradient of the average reward. And now it appears that we have an expression for this. Now, the next step is there's this trick that, we know that this expression, like the average reward, because of this, we're still under this assumption here that the average reward doesn't depend on any initial starting state. It only depends on the policy. So we're going to make the claim that the right-hand side of this equation here should not depend on S or any particular state that you are in. Now, if something is independent of S, then we can actually take the sum of that thing with any probability distribution over S, because then the thing that doesn't depend on F, we can factor out of the sum, and then it's equal to F. So it's the same trick we did here. We factor this out, and then the remaining sum over pi just equal to 1. You can see if we have F not dependent on S, and then if we take any sum where, mu could be anything as long as the sum over mu is 1, then these expressions are all going to be equivalent. So here, we're just taking the right-hand side, and we're computing this sum over this weighted sum of mu, where mu is the steady state distribution under the policy, right? So here, the claim is that this expression is equal to this expression because this entire expression doesn't depend on S. So then you can start separating these sum terms out. And there's a little bit of algebra here, but this middle term is what we're interested in, because once we swap the order of the sums, we actually get something on the inside here, which if you compare it to this expression up here, right, this whole term reduces, right, this sum over S of mu and the sum over A here, this just reduces to the steady state distribution of S prime by this relationship. And again, this was derived in chapter 9, but this sort of like recursive expression for the on-policy distribution over states. So, once you replace this with now the steady state distribution at S prime, these two terms are actually equivalent because, the sum variable that we're summing over is arbitrary. Where was I? I think I was explaining that this sum term ends up being equivalent to this term, so they cancel out, and you are just left with the first term here, which is the sum over the on-policy distribution of this. And then using the definition of of the expected value, right? This, you can just replace the sum over the on policy distribution with an expected value, because this is the definition of the expected value, right? It's just the sum over the likelihood of being in a state, right, times the thing you're computing the expected value of. So that is what appears here. And then this is now we're back in the same sort of trick that we did with the first policy gradient derivation, right? Where we multiply and divide by the policy. And, the purpose of doing this is now we have this again, a sum over actions with a probability of A. And we can also, since this is already inside of the expected value operation, we can also consider just taking a sample of this instead of taking the sum over the probabilities. This is just the same sort of application of the expected value definition. So here, A is being replaced with whatever the action is at time step t. And then similarly, we can replace the differential value function here with, so I mean, this could go either way. Like here, I've replaced it with the actual differential return, right? And then, this, we just say, we can always write this as the gradient of the log of the policy. So, this G, in the case of the Monte Carlo method, we just actually used this G. I mean, we just need something which is an estimate of the state action value function. So it could be G. Since we're dealing with continuing problems, we won't have this. So we're going to have to use some bootstrap estimate, which typically what we would use. Sorry, I should probably refresh this. So okay. There should be an R bar here, but this is always this is like the differential version of the bootstrap estimate. In the case of discounting, we would take the reward plus gamma times v prime. Here, instead of gamma, we're taking R. I'm just going to refresh this so hopefully the R bar shows up. But it should be R minus R bar, where R bar is some estimate of the average reward. And yeah, you can see here in this pseudocode, it's like we can't develop a Monte Carlo technique for this. So we're just going to skip straight to the actor-critic methods with eligibility traces because they're the most general technique. And here you can see, right, this is the estimate for the differential return. And here the delta is we're using our estimate of the differential return at state S minus the current, differential value estimate at state S. Let's see. It's going to show up now. Yeah, okay, yeah. So say we have R minus R bar. Yeah, so this is the target value, all right? So the delta is going to subtract the target value from the current state value estimate. So everything else, like this is going to mimic the continuing methods from before, where we have to keep some running estimate of R bar. Here we're going to update R bar actually with delta instead of just with R, because it ends up lowering the variance of the estimate. And then everything else about the algorithm looks exactly the same as the previous actor-critic methods. Right? We just, end up replacing this delta. Like the only difference is we have another learning rate parameter. And we also have, right, this update of R bar. That's the only difference, but everything else is the same. And so here, the way I define like all the previous methods, it was pretty generic. So, once I define this new version of the Actor-Critic with eligibility traces, then like all the arguments here are the same as before. The only difference is there's this extra keyword argument for the average reward learning rate. And then previously we had at the very end, I said I allowed both like a maximum number of steps and a maximum number of episodes for the problem. So here there's no, sense in having a max episodes because, the way this is defined, there should never be the end of an episode for these continuing problems. So there's just a max step argument, and then otherwise everything else. So as long as you call this function and you just don't provide an argument for max episodes, then everything else will be the same. All the previous estimation techniques can just be applied to this. You can see I've added this condition here so that, the way that MDP is defined, there's this check you can apply where, like to see if a state is terminal. And if you ever encounter a terminal state while using this algorithm, right, that shouldn't happen. In fact, the algorithm wouldn't even know what to do because from a terminal state, you shouldn't be able to transition to anything. So no future steps should be possible. So here, what I've done is just like, if you ever encounter a terminal state, it just errors out. So we could see that if we try to apply this to the corridor grid world example, right, this was the first example in the chapter, right? We had this short corridor grid world with switched actions. This was an episodic problem where as soon as you reach this rightmost goal state, the episode terminates. And there's a reward of -1 per step, right? So if I try to apply this technique to this, you'd see like it encounters state 4, which is a terminal state, and this algorithm should only be applied to continuing tasks. So, if you do want to test this on this kind of problem, we can always reframe any episodic problem as a continuing problem. You just have to change the reward structure a little bit. So, here what I've done is all the transitions are the same. I'm still keeping track of the goal state, but now instead of getting a reward of -1 per step, I'm going to assign a positive reward at the goal. Okay, so you get a reward of 0 on every transition. This is saying, but if you are at the goal, then you get a reward of 1. And also, sorry, another thing that should happen is, yeah, so if you reach the leftmost limit or you reach the goal, then the state should reset to 1, right? So normally when the episode ends, you would restart at state 1. Here, it has to be part of the actual, transition function. But so when you would end up in a terminal state and reset the episode, instead of resetting the episode, you get this positive goal reward. And then the transition state, instead of being state 4, will actually be the starting state of, where the episode should start. Yeah. So does that make sense to people, like how to reframe this problem as a continuing problem?
Yeah, that makes sense, Leon, by making a episodic problem into a continuous problem by having a transition state from the goal back to the restart point, and then having the goal being a positive reward instead of -1 reward for every single state.
Mm-hmm. Okay, good. So, yeah, so now, like I had showed this parameter study or in a previous meeting for this. So here I'm just defining a bunch of functions here that will perform a parameter study sort of over. In the continuing problem case, you have to consider even more parameters than usual. in this case, right, like we have lambda for both the policy parameters and the value function parameters. And then we have this learning rate for the average reward, which hopefully doesn't end up mattering too much. Like practically changing this shouldn't affect things. And then in the parameter study, we're just going to test the performance of this over a bunch of learning rates. So here you can see like the actual value function learning rate doesn't affect things too much, but we actually, I move this around a bit. You can see how the performance changes as I change the values of lambda. But here, this seemed to work better when the policy, oh, let's see, so this was 0.063. Yeah, so it's a little higher. So like this seems to do better when the lambda for the policy parameters is doing a little less bootstrapping and a little more averaging, future rewards, right? As lambda approaches 1, this becomes closer to a Monte Carlo method than this. So, yeah, so this works. And then, I'm sort of selecting one of these same sort of parameters here. And you can see training this over a large number of steps. Again, this is like what we did before is we start with a bad parameter initialization. We can see, we know the optimal policy where this is the probability of the right action should be about, 0.6. So whatever, this is overshooting it a bit, but it's in the right realm. And if I run this, a few times, you can see it's converging to about the right value. Maybe, the learning rate should be a little lower. So yeah, you can also, but yeah, this is like the range of what the probability of the right action should be in the optimal case. So you can see that this problem, we had already solved this as an episodic problem, and now it's also working as a continuing problem. So the next thing I was going to do is try to apply these continuing methods to a few other problems that are not in the chapter, but they're ones that I had looked at previously. So one of the advantages of this technique is there are certain problems, like if you recall, let's see if I can pull this up, but the mountain car problem, see, this was from chapter 12. Actually, let me see, where is, yeah. So we had the mountain car problem from chapter 12, right? It had solutions like this and like value functions like this. So you can see in this value function, like because this problem gets a reward of -1 per time step, you end up getting, value estimates that may, like the values get kind of large because it depends on sort of how long the episodes are. And for some function approximation, it may be a bit of a problem to produce values this big, especially in the early parts of training. You can start getting diverging values. The nice part about the differential value function, where we have should they have it here? I guess I don't have the definition, the differential value function, but I'll pull it up here. Is that we're always subtracting the average reward. So it does keep the values kind of in a reasonable range. So it may make certain problems easier to solve. We can certainly try it on the mountain car problem and see what happens. So here, let me just show. Oh yeah, the corridor problem. And so, yeah, that one example was the mountain car problem. The other problem I had looked at was the cartpole problem, right, in chapter 12. And we had solved that with, again, these value function methods. So, here was the cartpole problem. And we had created this, simulation environment and then tried to solve it with a few different techniques. When we did it before, and this was using tile coding, the most successful technique ended up being this some sort of dynamic programming version of sort of Sarsa Lambda. But we did end up getting a solution, and were some of the parameter studies here. You can see, like, the cartpole problem we had defined as an episodic problem, right? Where, like, we would start with the pole up, and then if it fell past a certain threshold angle, then it was considered a failure, and the episode was over. And it would get, in this case, a reward of +1 for every time step in the episode. So the training was supposed to extend the length of the episodes. Now, for a perfect policy, the value function would have infinite value. So because it should be able to stay up forever. So, I mean, but if you have a policy that's already actually successfully able to get that high value, it may not be a problem. But we can reframe the cartpole problem. Like here, these are all the functions that just define the dynamics of the problem. And, here is like this failure case where we can define a failure in terms of any of the four state variables. So, like, the state in the cartpole is the x position. Actually, wait, I can show an example of. Let's see, do I have an actual episode? Oh yeah. So here's a test episode. So here we have all these states, right? And the cartpole state is defined in terms of four values, where the first value, this is just the x position. Theta, this is the angular position of the pole in radians. And then there's the velocity of both of those components. I also have this time step t as just part of the state to make it easier, but I'm not actually going to use the time step as part of the state value representation for solving the problem. So, this was an episodic problem. We can reframe it as a continuing problem. And here is making this, continuing step version of cartpole, where now, if it normally, would have been a failure, what happens instead is we initialize a new state. And I do have to actually sort of inject to make sure, like, the time step keeps incrementing. This is just sort of incrementing, keeping track of the time step of the previous state. And then there's a reward of -1 if there's a failure. Otherwise, it's just a reward of 0, and it does the normal state transition. So it's the same kind of thing we did for the corridor grid world, where I just make this a continuing problem. And then, I'm making here a continuing version of this MDP, right? So, previously we tried doing tile coding. Tile coding is just a method of forming feature vectors. In the case of the cartpole problem, there are these four different relevant state variables. So with tile coding, we partition the state space in all these different dimensions, and the number of features does end up blowing up with the number of features. So in the case of the mountain car problem, there were only 2 features, which was the position and velocity of the car. But in the case of this, there are 4 features. So this is defined at the size of each of the 4 tiles. And then here I'm only using 8 tilings, but you can see that there's already, 53,000 features already just for this. And I'm intentionally not using as many partitions in the x direction, because if you think about the problem, this problem is defined so that if the cart goes too far in either left or right, on the track, then it's also a failure. But the actual physics of controlling the cart, it doesn't really depend on where you are in the track. It's only relevant when you get too close to the edge of the track, right? So you shouldn't need that much information about the x position, which is why here it's, you know, there's fewer tiles in the x direction, which just means there's less information in the x direction. So here I'm just showing an example of a parameter study, again, affecting all these. I've tweaked this a little bit. It seems like this does better when, again, like the policy value of lambda is closer to 1. And there's a lot more bootstrapping in the value of lambda for the value estimation. So here you can see like it's not that clean of a parameter study. Like there is some kind of trend here, but it also looks kind of noisy. Like it's unclear if this is actually a good learning parameter. This is an example of actually doing this training over. So here I've extended the number of steps to 100,000. This parameter study is only over 10,000 just to get a sense of what region of the parameter space we should be in. So here I'm doing the training over 100,000 steps. This is plotting the average reward through the training process. So you can see that for the random policy, the average reward per step is about negative 0.034. So if you divide that, if you take the inverse of that, it's about like 30 time steps. So if you don't do anything, if you just kind of move randomly or don't take any action that makes sense, the pole ends up falling in about 30 time steps, which in this case, the actual time step unit is 0.04 seconds. So it's about 1.2 seconds on average, the pole stays up. So through this training process, you can see it's lasting longer. Like here's an example of applying this policy to a cart. This is showing the 4 different state value parameters of the cart. And you can see like depending on how it's initialized, and there's some, the policy is somewhat stochastic, you can see it does affect what happens, but it is consistently staying up longer than like 1.2 seconds. But it's not that much longer. We can see what is actually causing the cart to fail is the pole angle. Like it's falling too far. It's not actually getting too far out in the x direction, right? This is only a value of -6. So the other thing you can do here is sort of visualize what the policy is. So here, because now these are policy gradient methods, right? And there's 3 actions in this case. So the 3 actions, what's being shown here is the policy, probability distribution for each of the actions, and I'm fixing the x position and velocity, right? So this is just showing at the start, so when the cart is in the center and has no horizontal velocity, then this is showing the policy function over the pole angle and the pole angular velocity as that changes. So the closer this value is to 1, that action is more probable. And if you look across all 3 actions, these values have to sum to 1. So you could see this whole region where it's like 1/3. That just means that this policy doesn't have any preference for the actions. Yeah, so this is showing the actual policy distribution in the center here where this x is, where the favored action is 0, because you can see like right where that x is, this heat map has a value of 1. This is showing the differential state value function. So, it's clear this is like somewhat successful, but it's not that successful. Like the pole is not staying up for like a really extended period. So the value function looks a little weird. It's definitely not, like perhaps the tile coding is not quite up to this task. You can see also here, as I change the X position, it should have, oh, wait a second, am I actually, okay, never mind. This isn't actually set up to do that. I'll show that in a later plot. So, here's the value function. It does look a little noisy, right? Like we have very rapid changes from 1 probability to 0. But, we have clearly some success in this training process, but not that much. So, tile coding may actually, run into problems where you have this many state variables. Because, right, like we already have, 53,000 features is quite a lot for a problem this simple where we're not training it for that many steps. So another approach you can take is just go for some kind of nonlinear function approximation. So here, I already have these functions defined for applying just a simple, like fully connected neural network to this problem where there's just here, I'm just doing it with 2 layers. Each layer just has a size of 64. So what this network is doing is the network's actually being used for 2 purposes. Like there's one output layer which computes the policy function, which here is a probability over the 3 actions. And then the other output is being used to output the differential value function. But it is sharing the hidden layers in the network. So here, this parameter study looks a little more clear cut with some kind of trend, because here, right, this is the learning rate for the value function parameters. You can see it's in the middle of these 2, and then this value is in the middle. So this is showing the same kind of training thing, just kind of selecting some of these parameters. So here you can see I'm selecting both. Here, both learning rates happen to be equivalent, where it's about 0.03 for both the parameters, the policy parameters, and the state value parameters. And these, they're similar. The values aren't quite as extreme, but theta favoring higher lambda, W favoring lower lambda, and same hidden layer structure. And this is showing the training process over, I guess, how many time steps is this? Oh, this is over, okay, 300,000 time steps. But you can see it's very smoothly improving right here. Actually, we don't even see the part where it was 0.035, right? This. Oh, it's actually worse. Okay, so in the early parts of this training, something about the neural network, it's actually the randomly initialized network is quite a bit worse than the random policy here, at least, in the early part of training. And then it quite rapidly improves to something quite a bit better than what we got with the tile coding. Also with a lot fewer parameters, actually. Like we don't have anywhere close to this, 53,000 parameters here with just this 2-layer network. So we can visualize things the same way. We can see that this training actually, essentially solved the problem. Like here, I'm cutting this off after 1,000 steps, which is about, 30 or it's 40 seconds. But, this, at least the pole has not fallen in 40 seconds. We can see that the oscillations are getting a little bigger. This blue line is the X position. And we can see every time it goes, it is getting a little closer to the edge. I'm not sure if I actually let this run for longer, if it would. Okay, well, it hasn't failed yet. This is still getting, but I believe that this will still fail after a much longer number of time steps, just because, yeah. So here, it's failing because it actually hit the edge. But probably if you did this training, if you repeated it a few times, you would find policies that don't have this property where it's getting closer and closer to the edge. So it's mostly figured out the problem. Here we can isolate some of these. So here's the angle, and see the angle is not the problem here. It's staying. I mean, this is. I think that the failure angle is it's 70 degrees. So that's let's see, 70 degrees is 1.2 radians. So we're still well short of having a failure angle here. And then we're also, the velocities are all pretty under control because, right, this can go up to 50 without having a problem. These are within that range. And then this can go up to 10 without having a problem, and it's staying under 3 all the time. So this is at least 1,000 steps of this episode that was run with this policy. And here we can also visualize the episode a little differently. This is just showing each time step the actual like pole angle and the different velocity metrics, and also what action is being taken by the policy. We can see I can't it won't move like that quickly, but here like we can see the pole is starting to fall to the right, but at the same time we are accelerating to the right, which is then reverses the direction of the pole. And now as the pole is going to the left, it's going to sort of shuffle back and forth rapidly to keep the pole upright. And then this, I had already shown, right? These were the actual functions that it found with tile coding. And these are the functions that the neural network found. You can see they actually mostly look linear when you break them down like this. These actual surfaces look fairly linear, but it's hard to see exactly what's happening in the higher dimensional space. Like these are sort of slices through a fixed value of x and x dot. But as I move this episode around, the value of x, so you can see like at the start, the position and velocity are both 0. And as I advance the episode, these values are going to change in here, as well as the angle. The little x here is showing, where in the in this phase space or in the state space we are for the policy. So see here both. I mean, so this x is showing the angle and angular velocity, and then the entire heat map is for whatever x and x dot is. So here you can see as the pole angle is going to the left of center, and I'll go back a little bit. And the velocity is, somewhat close to 0, but the pole angle is left of center. So here we're in the part of the policy space where we are going to the left, right? So we're accelerating to the left, and you can see here in the policy heat map, right? We're in the part of the heat map where action 1 is heavily favored. See it here too, right? So we have about a 74% chance of taking the action where we accelerate to the left. And then, right, this is near 0, and this is near 0. And you can see as we go more extreme in the pole angle to the left, it more heavily favors the action of accelerating to the left. The other thing you can see here, I'm showing the same policy plot, but instead of looking at the actual episode, I can just change all 4 of the parameters of the state. Right, so here it's just everything is close to 0. I'll actually make it 0. You can see, so when the pole is roughly centered and we're at 0, it's a little bimodal, right? But it sort of will rapidly alternate between going left and right. Now, the shape of this heat map will change as I move. So like I said, like the x position shouldn't actually matter too much for the policy, but it does know that if it gets too close to the edge where x is 50 or negative 50, it does need to avoid that. And it is doing a fairly good job of avoiding that. We can see that if the episode goes on too long, it will actually get close to the edge. But we should be able to see how the policy is affected by the x position. So here it's centered, and we have, again, like these lines that mark the transition point from going left to right, or sort of, have these diagonal lines that go through the center fairly clearly. Now, as I move x to the right, so now I'm moving like closer to the right edge, but still everything else is 0. So it ends up shifting the policy over where it actually favors going to the right, or accelerating to the right, which is actually going closer to the edge, which is a problem. However, the reason for this is because accelerating to the right is a way to get the pole to tilt in the left direction, and then you could slowly move to the left, and then it's a way of repositioning yourself more to the left. But it's like you have to kind of rapidly accelerate right in order to actually make your way left. Like, you should be able to see that happen in the actual episode, where, like, as we get close to this right here, the x position is we're getting close. I mean, here it's not actually getting that close, so it doesn't affect it too much. But as we get close to the left edge, the car ends up, like, if it didn't care at all about the edge, right, it would just sort of drift over to the left, and it might just keep drifting, kind of like it does in the case of tile coating. Oh, wait, actually, in the case of tile coating, we don't really see that because it never gets. Yeah. In the case of tile coating, the problem is the pole actually falls down too early. But, in this case, we can see that the cart ends up does like repositioning itself more to the center. Clearly, it doesn't do a perfect job of that because these oscillations are going to grow over time. But perhaps if we recompute this episode for longer steps, that there are probably cases where it doesn't actually run into a problem. Let's see. I mean, it seems like, yeah, in all cases here, these oscillations are growing. Yeah, in most cases. Okay, yeah, but different levels of success depending on how the episode is sort of randomly initialized. But over a short enough time span, this is keeping the pole up. And then similarly, if you move closer to the left edge, right, it shifts the whole policy over and it starts favoring accelerating to the left so that it can reposition to the right. And of course, I guess we should also see the value function. Values get lower. Again, these are the differential values. They're not actually the correct values. They just have to be correct relative to each other, because these values should actually all be negative, because we only have failure cases here. There's no positive reward in this problem. But as we go more to the center, yeah, you can see, like, the values are closer to 2, and then towards the left edge, they're on average lower, which we would expect, because if we're closer to the edge, we are closer to a failure case, right? Either the left or right edge, right? Here, the right edge, the values are quite a bit lower, around 1, again, in the middle. And similarly, if we change the velocity, should have a somewhat similar effect. So we can see that, right, changing the velocity alone without this, it doesn't actually shift these policy functions that much. It does, though, reduce the value here, right? As we go to these extreme, right, rapid speed to either the left or the right versus the value in the center, be closer to 2. Yeah. So are any questions about the cartpole problem and these different value and policy functions? because the next problem, again, revisiting this mountain cart problem, but I'm actually going to do that more in the next section on continuous actions. Actually, with cartpole, so I don't think in this previous chapter, yeah, I don't think I did cartpole. Yeah, so here, like the tile coding actually did work for this technique. In the case of policy gradient, it is a different technique. This clearly is close to what the optimal policy function is. So clear, like the tile coding clearly has a hard time, forming these shapes, or at least has a hard time forming these shapes where they actually shift correctly to the left and right as you change this x position. But we can see sort of some evidence of these shapes forming, but clearly like the edges here, like the action should not be just random at these extreme pole angles. In fact, the extreme pole angles are really where, if you compare this to the neural network policy function, right, the extreme angles are where the policy becomes very deterministic, because those are the angles where you really have to take a decisive action to make sure the pole doesn't fall. So this has clearly learned some of those decisive actions at the less extreme angles, but then as you get, I think it's probably just because with this many features, this probably just needs to train for a lot longer period of time in order to get this correctly. But with tile coding, it's already kind of inefficient because we have to form so many features with the 4 different state value variables. So the only other remaining section in this chapter is this section on continuous actions, and there's some derivations, but no actual examples here. So we can look at, I did actually implement the policy gradient technique for continuous actions, but in order to understand it, you do first have to derive certain things. So, one of the simplest ways to do continuous actions where, like, so to be clear, for the cartpole problem, right, we have these 3 discrete actions. And we've already figured out, what is a reasonable value for the acceleration either to the left or to the right. And all the policy can do is provide a probability for each of the 3 actions. Right? So here, this means like 90% of the time, it would accelerate to the left at whatever that fixed value is. The idea with the continuous actions is that maybe, we have some action space, which let's say is the entire real line, right? So in a simple case, it's just a single number, but it can be any real number. And then, in that case, we could try to, the easiest way to provide a distribution over that is to pick some fairly, common, simple probability distribution, like the normal distribution. And right, this distribution is defined by 2 parameters, by the mean and the standard deviation. And it controls the shape and position of the distribution. And the idea is that the policy function would then output a value for the mean and variance at every state. And then those 2 parameters would be used to construct the probability distribution here. So this is saying, you have a policy function, which is a function of the parameters theta. But really, the way it's a function of the parameters theta is that we're saying mu and sigma are a function of the parameters theta. Right? And then when we go to sample an action from the policy, we just tell however we're sampling that what this policy is outputting parameters of a normal distribution, right? So here, like in the linear case, we would have, a vector of parameters that represent the mean, and then the mean would just be the inner product of that with some feature vector. And then Sigma, because sigma has to be a positive value. So if we're going to do a linear method where we just want to take this inner product, instead of forcing this inner product to be positive, we'll just apply the exponential function to it. So now, right, this maps, right, the entire real line to just only positive real numbers. So that's what we want. And then we do need to be able to compute the eligibility vector of this, right, which is the gradient of the policy with respect to the parameters. And in this case, there's sort of two sets of parameters, one associated with the mean of the distribution, the other associated with the variance. And there's this exercise to show the actual, functional form of the eligibility vector. Yeah, so this is sorry. So yeah, they have this diagram. I'm just like, if you have the normal distribution here, right? Like the mu just controls the position of it here, but it is completely unrestricted to the whole real line. So it might be a problem for certain problems. Like you have to be able to handle the real values, right? So here's, right, as the standard deviation goes bigger, it just broadens out. And like the reason why, right, we're not just outputting a mean value is because we need, like, our policy needs to be stochastic so that it doesn't get, I mean, like the whole point of the policy gradient methods is that we can have a stochastic policy, right? If we didn't use this parameter, this normal distribution with mu, like if we just outputted a value of mu, then we would just have a deterministic policy that outputs a real number, which, I mean, it might work okay, but we're back in the realm of not having stochastic policies anymore. So this is to ensure that we actually have a stochastic policy. And if a deterministic policy is more favored, then it would just learn to shrink the sigma value closer to zero. So it effectively becomes a delta function where all the probability is concentrated around mu. Right. So we can do, this exercise 3.4 asks you to actually derive these components of the eligibility vector. So maybe we'll go through that, and then we can, maybe save the rest of the treatment of continuous action spaces and maybe some other, bonus problems for next time. Because there are some issues you run into with the continuous action spaces, like, in the case of the cartpole problem, we have this value to your F max. So this represents like what the actual acceleration force is when you take the action where you accelerate to the right or to the left. So there is this value F max. Now you probably want to rescale this so that like when you're outputting these continuous values, it doesn't have to like go all the way over to this extreme value. You can just rescale it so that it, like a value of 1, you just multiply it by F max. So basically, like if the distribution sampled a value of 1, it would be the most extreme, and then -1 would be the other extreme. But there's nothing to stop the distribution from outputting, a higher value. And in fact, even if the distribution is centered here, there's some non-zero probability of sampling a value here. So you do have to adjust the step function. Like if you don't intend it to be possible to apply a force bigger than this, then you have to then clamp the value so that even if the distribution outputs a very high value, it doesn't actually accomplish anything. It's just the same as outputting the maximum value. Or you can make it even more punishing, where if you output a value that's too large, you can have it like slip or something. So you say it actually applies less force if you overshoot the maximum value, and then hopefully it would learn to not apply. But it does have to, like, in a sense, learn what the force limit is on the problem, whereas in the discrete case, it doesn't matter because
Well, I guess, that would make sense given that I guess in anything that's robotics, then there would be a limitation of, how fast a motor can spin, based on the limitation of the motor or something like that, or any hydraulic piston,
Hmm.
some other
Yeah.
physical component would have physical limits.
Yeah. And that's why, like, practically a lot of the time, you do just want to use a discrete action space because you already know, like, even like the voltages you can apply might have discrete steps to them. And if you really use a continuous action space, it may just be too like unrestricted for the problem. I mean, you can see some of that in the actual solution that you get if you try to apply this like to the mountain car problem. But for now, maybe we can just try to derive this expression for the normal distribute for the eligibility vector just to see. And then as a bonus, in order to deal with this issue of covering the whole rail line, there are alternatives that you can use to the normal distribution, which might be useful for certain problems. But for now, let's just look at this first exercise 3.4. So, here's the policy function, right? We have normal distribution, right, with mu and sigma, but now both mu and sigma are functions of theta, right? Where theta are the parameters. And we're going to assume also this linear parameterization of mu and theta, right? Where sigma is just the exponential function applied to this dot product, and mu is just the dot product. So, eventually we're going to need the gradients in terms of mu and sigma, so we can just compute it now. Like the gradient of mu in terms of the parameters is very trivial. It is just the feature vector, right? The gradient of sigma, since this is an exponential function, it's also fairly simple, but it's just sigma itself times the feature vector, right? It ends up being, right, this is just the definition of the derivative of the exponential function with the chain rule. Um, yeah, so I'm also gonna, to simplify the expression a bit, I'm gonna write this function f of mu and sigma, which is just this piece in the parentheses here. So this is just what the exponential function is being applied to. So, this will then simplify in writing it down to the exponential function applied to f, and then we have the 1 over, sigma part here. So now, if I move the 2 pi over here, I just end up, this is just applying the chain rule and the quotient rule to this. Actually, no, in this case, it's just the chain rule for now. But, here's, yeah, chain rule being applied, and then I'm replacing the gradient of sigma, right, with this expression, and which I already computed up here. And then, we have this simplified expression, but what we still have to compute here is the gradient of f, right, where f is the thing inside of the exponential function. And it's just, more algebra, but what we're going to end up, I already know that mu and sigma themselves have their own gradient. But for the purpose of this calculation, we're just going to apply the quotient rule here, right? So we have 1 over, right, sigma to the fourth is just part of the quotient rule. And then we have these derivatives, right, where the 2 also just comes from the square term here. But we also have to remember that we still have to compute, keep track of the terms which are the gradient of mu and sigma. So here, eventually on this step, I'm just replacing the gradient of mu and sigma with what I computed up here. And then we end up with this expression for the gradient of f. So I just replace this up here, the gradient of f, and now I've removed all the gradient terms. The only thing left are these feature vector terms. Keep in mind that the actual policy function is this expression, right? It's 1 over sigma root 2 pi times this. So, part of this can actually be right. If I divide back out by the root 2 pi, this actually just turns into the original policy function. So now we have an expression for the gradient of the policy. And remember, the eligibility vector is just that divided by the policy itself. So this term cancels out. And then we just have these two terms here, which, let's see, what is the expression that we actually are supposed to get here? Yeah, so this will cancel out. Here I'm summing them together. Here they have it written as two separate things, but it depends on how the feature vectors and parameters are actually organized. But here that's sort of like saying that these are completely separate feature vector parameters. But if you were to sum them up, if you imagine that that the x's have components that are not connected, because this gradient term is actually computing the gradient in terms of each component of theta here. Yeah. And yes, this is still in the linear case. But yeah, this, like, writing it like this is like as if the parameters were concatenated together, right? So when you do this sum, you imagine summing the components where the ones that apply to mu would just be on the top part, of the ones that apply to sigma would be under it. Or you can write it separated here, where whether they're actually concatenated or they're just entirely separate vectors, you end up with the same expression. Yeah, this exercise I'll probably leave. I'll just make one other comment about an alternative to the normal distribution. So if you want a continuous distribution, like over the real line, which respects some range of values, you could use the beta distribution, because the beta distribution, the random variable only ranges from 0 to 1. Now, the shape it's a 2-parameter distribution. So normal has mean and variance. The beta distribution has alpha and beta. And the way they affect the distribution is not as straightforward as the Gaussian. Like, you can see that when they're actually of equal value, it has this bimodal shape. And then, if they're less than 1, then when they're, here they're both equal to 2, and it's more of a unimodal shape. But I have this, so here's the beta distribution, and you can see how it changes. So if beta is, if they're both close to 0, you get this bimodal shape, which probably would not be useful for most policies. And then, as alpha goes, well, here, even if alpha is slightly above 1, it ends up, all being concentrated on this one side. And then vice versa, if you keep alpha close to 1 and you increase this, you end up making the distribution favor 0. And then as they both are equal in sort of some middle value, you get something more in the middle, which does look more like a Gaussian. I think it should get narrower as we move both of these. So there's a way to shift the distribution back and forth, like to a point, right? Like this at the extreme will still be centered at 1. If you want to then move it further to the left, you then have to start moving beta closer to 0. But there is a way to shift this distribution around. But the nice thing about looking at these distributions is if you look here at the maximum likelihood estimator, right, which is a very common thing to calculate for probability distributions. In order to do the maximum likelihood estimation, we need to calculate the derivative of the log of the distribution with respect to the parameters. And if you compare that to the eligibility vector, right, if pi is the distribution we're using, we need this in order to compute the eligibility vector, right? We need the gradient of the log of the distribution. So as long as we use the chain rule and we know that like alpha and beta are then functions of theta, then we can use this formula and figure out, where the gradient terms with respect to alpha and beta are. And if you do that, like this is what the eligibility vector looks like for the beta distribution, right? I'm just here using what the maximum likelihood, what these partial derivatives are here. And then, there's a little bit of magic here because, right, this is written in terms of this phi function, which is the digamma function, which, luckily you can look up implementations of this function, but you can see I've written it out a little more explicitly here where, yeah, phi is a digamma function. But here, this is the eligibility vector in terms of the parameters associated with alpha and then with beta. And this is also in the linear case, right, where I have, also for the beta distribution, the parameters alpha and beta are restricted to be greater than 0. So it's kind of like sigma for the normal distribution, right? So I'm going to apply the exponential function to both alpha and beta here to the inner product. So then the eligibility vector, if I separate out the parameters for alpha and beta, it just has these two pieces. They look very similar. The only difference is there's an alpha being multiplied here and a beta here. And then, here we have the digamma function of alpha and beta. These two pieces are the same. So this is an alternative distribution that you could use. The advantage would be that using this guarantees that the sampled value will be between 0 and 1, and then you could then remap that to any range you want. But I do have some examples of using this. So you can then use this continuous action space on any of the techniques from the chapter. So it would apply to the episodic techniques with reinforce and the policy gradient technique. And then it would also apply to the continuing techniques we've been doing for most of this chapter, where you use the differential values. So I guess for the next time, I can show how the continuous actions could be applied to some of those problems, and we can compare the solution techniques. Across. We can compare a lot of the techniques with, continuous actions, episodic, continuing, and see what has the most success on a couple of these problems. And then, we'll probably think of a few more problems to look at, because at this point we have covered all the major techniques in the book.